All right, so in chapter one, we studied how to design a statistical study. And in chapter two, we talked about descriptive statistics. And now we're going to talk about probability. So actually, the next three chapters, including chapter three, are going to be related to probability. And then we're going to combine the concepts of probability with descriptive statistics to do a little bit of statistical inference. So, to start, we need some basic definitions for probability. And the first is, when we talk about probability at first, we're going to talk about a probability experiment. And a probability experiment is an action or trial through which specific results are obtained. So, there's a lot of different things that are probability experiments, but the most common ones that we're going to talk about, at least in this class, are situations that you're familiar with, such as flipping a coin is a probability experiment because the results that can be obtained are heads or tails, or rolling a die is a probability experiment, spinning a spinner, drawing a card from a deck of cards. All these things can be probability experiments. And a single trial from that probability experiment is known as an outcome. And the sample space is the set of all possible outcomes from that probability experiment. Now, many times you might refer to an event where that event contains more than one outcome. Or it could just be one of the outcomes. So what we're going to be asking about is we want to find the probability of a specific event given a probability experiment. So the first type of probability experiment in this first example is tossing a coin, tossing a different coin, and then tossing another different coin. And then we want to identify what the sample space of the experiment is. So when we toss a coin, we can get heads or tails. When we toss another coin, we can get heads or tails. And we're doing this a third time. And the tree diagram just helps us visualize what's going on in the probability experiment. Now, with tossing a coin, you may not need the tree diagram, but trust me, a tree diagram is very helpful, especially later on. So, the sample space for this probability experiment is you can get three heads, right, on all three coins. And if you look at the path, the top path is that outcome, heads, heads, heads. And we can get heads, heads, tails, heads, tails, tails, or excuse me, actually heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. And there's 8 outcomes. And if you were to follow each path of this tree diagram, you should be on one of these outcomes. And the sample space is a set, so notice how we put it in braces. And once again, there's 8 total outcomes or 8 possibilities here. So trying to make the tree diagram for this next one on your own, that consists of, the probability experiment consists of rolling a 6-sided die and then tossing a coin. And then see if you get the same thing I get. Okay, so hopefully you did this, and so when you roll a 6-sided die, you actually have 6 possibilities, 1, 2, 3, 4, 5, 6, and then each of these outcomes get heads or tails, right? So my outcomes are 1 heads, or I can get 1 tails, 2 heads, 2 tails, 3 heads, 3 tails, 4 heads, 4 tails, 5 heads, 5 tails, 6 heads, 6 tails. Now, if I want to get the total number of outcomes possible, there's actually a quick way to do this. And to do this, we can use something called the fundamental counting principle. So if I just take the number of outcomes 6 and multiply the number of outcomes for flipping a coin, which is 2, I get 12, right? And that's 12 total outcomes. You can do this too for this one. There's 2 ways to flip each coin, and I'm flipping a coin 3 times, so 2 times 2 times 2 is 8. And there was 8 total outcomes. So that's a nice little trick that might be helpful, and we'll do a few more examples of that in a little bit here. Before we do that though, let's talk about a simple event. So the simple event, an event is a simple event if it only consists of one outcome. So let's just read through each of these on your own and tell me if you think if it's a simple event or not. Remember, a simple event consists of only one outcome. So getting a 6 on a die, well, first of all, let's read the probability experiment. We're rolling a 6-sided die and then tossing a coin. So this is going back to actually this probability experiment right here, rolling a 6-sided die and tossing a coin. So how many of those outcomes has a 6 on the die? Well, that's not simple, because yes, there's one way to get a 6 on the die, but 2 of the outcomes in the full probability experiment actually had a 6. You can get 6 heads, or you could get 6 tails. So this is an important lesson learned here of it matters what the probability experiment is. If the probability experiment is just getting or just rolling the 6-sided die, then getting 6 on a die would be simple. But because you're also flipping a coin, there's 2 ways to get the 6 on the die. You can get 6 heads or 6 tails, because those are 2 separate outcomes. Okay, what about getting a 1 and then getting heads? That is simple. Getting an odd number and then getting tails, that is not simple, because there's multiple odd numbers. And getting heads and an even prime number, and you should know that the only even prime number that exists is 2. So another way to phrase this is getting heads and getting a 2. So this is simple. There's only one way that can happen. Okay. All right, so I kind of mentioned the fundamental counting principle a little bit, and this is something that I find a fun thing to do during class. But since this course is online, we can't really go through it. But let's say you're going, we're trying to decide what the meal is for the possible meals are for a senior banquet, and let's say we have 3 main courses and 4 sides and 2 desserts. Well, how many possible meals are there if I just have one of each? Well, we can use our fundamental counting principle and multiply 3 times 4 times 2, and we should immediately see that there are 24 different meals. Again, if I only eat one of each. Of course, many of us would not, right? We'd take, probably a couple sides, maybe sneak up to the dessert table a couple times. I know that's kind of my, what I like to do, but we'll see. Okay, so we can use this fundamental counting principle in a couple other situations. For example, let's say we have a license plate that consists of 4 digits followed by only 1 letter, and only odd numbers can be used for the first digit. How many different license plates are there? Well, what I like to do for these types of problems is draw a line for each character that we have. So for the first character, that's a digit, and the digit is only odd. Well, there's 5 odd numbers, right? 1, 3, 5, 7, 9. So I'll put a 5 here. And then there's 10 other digits total, 0 through 9. Everybody forgets about 0, by the way. So don't forget that there's actually 10 digits, 0 through 9. And those can be anything. And then the last one is 26. That is a, because that's the number of letters. And if I want to find out how many different license plates there are, we can multiply them. And the answer here is 130,000. By the way, if you had to do that in your calculator, you really shouldn't. You can simply multiply 5 times 26, right? Which to multiply something by 5, you just divide by 2 and then add the 0. So, for example, or move the decimal point over. So half of 26 is 13. Add the 0, so 130, and then I'm multiplying by 10 3 times, so I add 3 zeros after that. It's a nice trick if you didn't know that. An access code has 5 digits, so once again, I'll write my 5 lines. The first digit has to be 5 or less and cannot be 0. The last digit cannot be 3. how many different possible access codes are there. So try to figure out what you're multiplying together for this one and pause the video. So hopefully you tried this on your own, but there are 5 possibilities for the first digit, followed by 10, 10, 10, and the last digit can't be 0, so that's only 9 possibilities. And when you multiply all these together, that's 45,000 different access codes. This is why it's so important, by the way, to, when you have a password, to try to use, and maybe you've actually made a password and now computer programs are starting to become smarter with this, but it's so important, especially like if you have a banking password or email password, to use special characters, because if you think about it, there's 26 letters, and then if you can have 26 lowercase letters, 26 capital letters, there's 10 digits, and then there might be, I don't know how many special characters are on the keyboard, but let's just say there's another 10 special characters. I think there's more than that, but just for the sake of argument. Well, if I add all these together, that is 72 different characters for each spot. And the longer your password is, let's say your password is 10 characters long, 72 to the 10th power, that is a very large number of things that a computer has to go through to try to figure out what that password is if they're trying to hack you or something like that. Now, with that being said, generally a computer won't hack you this way. They'll use something called a dictionary code where they'll actually use actual words. So for example, if you have something like Fluffy22, because that's like your pet's name, and 22 might be, I don't know what that is, but might be your favorite number or whatever. That's probably not a good password, because people like to use their pets' names and their passwords all the time. It's just generally not a good idea. And it's an easy password to actually hack. So there's ways to actually, and if you want to, you can look it up, to make some passwords of your own. But I would advise, have a password that's long, at least 10, if you can, 15, 20 characters. Make sure it has caps, make sure it has lowercase, make sure it has numbers, and make sure it has at least one special character. And it's almost impossible to hack something like that, unless obviously you tell someone your password, which is always something that you should never do. But yeah, so that's an application for this, is because it would take a while for a computer to actually hack you, and the more possibilities are and the more you're multiplying, the more or the harder it is for someone to actually get a hold of your information, which is a worry nowadays. Okay, so using these concepts together, we're going to figure out types of probability. The first type of probability we're going to talk about is classical, and then we're going to talk about an empirical probability. So classical probability is simply if each outcome in a sample space is equally likely, and that is an important assumption we're making. Each outcome in the sample space is equally likely. To find the probability, we take the number of outcomes in event E and we divide by the number of outcomes in the sample space. So let's say we're rolling a two-sided die. Well, let's come up with the sample space, and this is going to take a little bit of time, but I just think it's so much worth it just to do it at least one time, because I know many people haven't really thought about this before. But if we're rolling a six-sided die, okay, if we're rolling a six-sided die, or two six-sided dice, excuse me, we can get two ones, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6, a 2 and a 1, a 2 and a 2, a 2 and a 3, a 2 and a 4, a 2 and a 5, a 2 and a 6, a 3 and a 1, a 3 and a 2, a 3 and a 3, a 3 and a 4, a 3 and a 5, a 3 and a 6, halfway there, 4 and a 1, 4 and a 2, 4 and a 3, 4 and a 4, 4 and a 5, 4 and a 6, 5 and a 1, 5 and a 2, 5 and a 3, 5 and a 4, 5, 5, 5, 6, and then 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. So this is effectively the sample space for rolling two six-sided dice. So if I want to find the probability of event A, we write it like this. The probability, capital P, of A, so the probability of A, and A is rolling a 3 on both dice. So I always like to think of the denominator first, and the denominator is how many total possibilities are there? Well, there's 36 possibilities, right? And we can use our fundamental counting principle for this, or you can count how many outcomes I wrote on the right side. But, 6 times 6, 6 for the first die, 6 for the second die, that's 36 possibilities total. And how many of those 36 possibilities have a 3 on both dice? Well, only one of them, right? This guy right here. So the probability is 1 out of 36. So using this sample space, try to pause the video here and try to figure out what the probability is for each of the other events. So rolling an even number on both dice, probability of event B. Well, there's 9 instances where there's an even number on both dice out of 36, which simplifies to 1/4. The probability of C, the sum of both numbers is 7. Well, there are 6 of those possibilities out of 36, which is 1/6. By the way, 7 is the most commonly rolled number on 2 dice. Probability of event D, both numbers rolled are the same. And the sum of both numbers is prime. This one's a little tricky, so to kind of write it out for you, the only numbers you can get that are prime when you add them together are 2, 3, 5, 7, 11. And if you count through all the possibilities, there's only one way to get a 2, right? 2 ones. There's 2 ways to get 3. There's 4 ways to get 4. There's 6 ways to get a 7, and there's 2 ways to get an 11. And if you add all those up, that's 15 ways, so the probability of rolling a prime sum is 15 over 36, which simplifies to 5/12. Okay? So that is an example of one probability experiment where each outcome is equally likely, and it's I think it's a good example to illustrate how to find just probabilities by thinking of a probability experiment. The next type of probability we're going to talk about is an empirical probability. An empirical probability is simply based off of the relative frequency of an event. And the relative frequency is f over n, which is the frequency of an event divided by the total frequency n. So let's do an example using relative frequency. It says a company is conducting an online survey of randomly selected individuals to determine if traffic congestion is a problem in their community. The results are displayed in the table below. So let's look at these results and try to answer the questions of finding the probability. Well, we want to find the probability that traffic congestion is a serious problem, and I don't have an event label here, so I'm just going to write the word serious here. So what's the probability of selecting someone who thinks traffic congestion is serious? Well, we need the total, and to get the total, we add all of our frequencies together, right? So when you do this, you get n, and in this case, the number is 320. So that's 123 divided by 320. And when you have a messy fraction like this, it's hard to interpret what that is. And so I suggest you have a decimal approximation for that. And if it's on a test or something, I'll tell you what I want the answer in. The fraction's best, but I always like making a decimal or percentage, especially when the fractions are like this, because a lot of people look at 123 over 320 and they don't really know what that means, right? So that's about 38%. So in other words, if I were to do this, ask 100 people, I would expect 38 out of those 100 people approximately to think traffic congestion is a serious problem. And we could do the same thing, but this one is about no problem. And similarly, there's 82 over 320. All right, and that's an example of empirical probability. Okay. Oops. So the next thing I want to talk about is the law of large numbers, and this kind of brings together classical probability and theoretical probability. And theoretical probability is basically, if you just think about what's going on, and what the sample space is, you can calculate the probability. Whereas empirical probability is based off of what actually happens in the event. Well, what actually happens, even if you did it over and over, it's not going to exactly match the classical probability. But the more times you do something, the closer the probability catches up to the classical probability, or the actual theoretical probability. So if you take tossing a coin 10,000 times opposed to just tossing a coin 10 times, we would expect the probability of getting heads, or I should really say the probability, or I'll put this in below it, proportion, because if we're tossing a coin 10,000 times, we're talking about the empirical probability or proportion. So the probability or proportion of getting heads when tossing a coin 10,000 times is closer to 1/2 than when tossing only 10 times. And that's because there's more variance when you toss 10 times, right? If you're just one heads off when you toss a coin 10 times, well, that's a difference between 50% to 60%. However, if you are only one coin off when tossing 10,000 times, well, that's a much smaller error. And there's an applet here that I found, the tossing coin applet. And I'll post a link to this for you guys so you can play with this a little bit. But let's just toss a coin 10,000 times. So my proportion is 50%. And if you toss a coin 10,000 times, this is the blue line represents the proportion of coins that are tails, it looks like. So we're looking at the proportion of head. Oh, I see. Green is tails and blue is heads. Okay, so if you do this over and over again, like that was 40%, this one is 60%, but there's a lot of variance here. Now, if we move it to like 25 times, it goes a little bit faster for us. If we toss a coin 25 times, again, a lot of variance, but you notice that there's not as much jumping around out here. And then if we move this all the way to 200, it won't let us go to 10,000. But if we go to 200, notice there's a lot of variance. But then as we keep tossing the coin, there's not as much change. And it's difficult to see in this one. This is actually a really bad simulation because it's almost like 10% above the green line. But you can see that it starts to level out more. Let's see if we can do this one more time, see if we get something a little better. And you can see that the line is gravitating slowly back towards the green line. And this happens every time. The empirical probability will always gravitate towards the theoretical probability, which is the green line, because the probability of getting heads, right, is 50% or 0.5. That's a good example there. A lot of variance here, and going up and down, and then comes up, and then actually gravitates back. So yeah, we'll do it one more time just for fun, because that's what we like to do. So you get a lot of variance, and then it just kind of shuffles along the green line after that. Okay, so that is one example of the law of large numbers, and this applies to anything though. Like, as more times you do something, you're going to approach that theoretical probability. Okay, moving on with probability though. There are some rules of probability that you should be familiar with and some other definitions. First of all, probability is always between 0 and 1. It always amazes me when I ever have questions on a test. And I get probabilities that are negative, or I get probabilities that are greater than 1. And that's just not true. If a probability is 1, it's certain. And if an event is certain, the probability is 1. And if an event is impossible, the probability is 0. This rarely occurs, by the way. For example, you might say to yourself, what's the probability, or well, let me ask you, like, think of something that, actually has a probability of 0. What has a probability of 0? It has to be absolutely impossible. And you might say, well, what is impossible might be, I don't know, something like the like getting an A in your next, I don't know, math class or something like that. If you're really bad at math, you might think that. Now, that's not actually impossible, because it actually could happen. Okay, so truly impossible or truly certain is better. Certain is a little bit easier. Like you might say for certain, like, what is the probability of the sun will rise tomorrow? Well, that's a certain event. It's 1. Well, it may not be 1. For all we know, the Earth might explode for some reason. Who knows? The chances of that happening are very, very small, so I don't want to freak you out or anything. But, it's hard to think of these things. Now, what is impossible is rolling a 7 on a 6-sided die. That actually is impossible. All right, and then this is pretty important. If an event is unlikely, it is typically said that the probability of that event is less than 0.05 or 5% or 1 out of 20. Okay. And that is going to come up later. So if something occurs, again, less than that amount, that's what we call an unusual event. Okay, that's an unusual event. And complementary events. Complementary events, the complement of an event are events that are a set of all outcomes in the sample space that are not included in the event E. And this is denoted by an E prime. It's also denoted, by the way, by an E superscript C, or you might see like an E -1. I've seen that before. But the book uses E prime. This is not a 1. This is like a little apostrophe thing almost. And it's called E prime is what we call it. And the reason why this is so useful is because the probability of complementary events, when you add them together, equals 1. And so you can get a bunch of results from this, like the probability of E is 1 minus the probability of the complement of E. And we will be using this in the next section for probability. So let's think about, I want you to think about the probabilities of these events and the complements of these events. And so pause the video here, try to do these, and then see if you get the same answers that I get. So hopefully you did these. So what's the probability of getting a 4 and then tails on the coin? Well, if we're rolling a die and then tossing a coin, the probability of event A, there's only one way to get a 4 and then tails, and there's 12 possibilities total. The probability of B, which is getting an even number and then heads, well, there's 3 ways to get an even number of heads, right? Because you can get 2 heads, 4 heads, 6 heads. So that's 3 out of 12, which simplifies to 1/4. So if I want to find the probability of the complement of A, that's the probability of A prime, is 11/12. And that's because 11/12 plus 1/12 is 1. So remember, the complements have to add to 1. So the probability of B is 3/4, because 1/4 plus 3/4 is 1. All right, the next thing I want you to do is on the very last page, and kind of just try to do this on your own. You can use the idea for the complement, especially for the last couple, but just try to figure out these empirical probabilities here. So hopefully you did these on your own, and pause the video and let's go over them. So we want to find the probability of selecting an employee that's between 35 and 44 years old. So there's 233 employees in that category out of 1,000. So the answer is 233 over 1,000, or 0.233. What about between 25 and 54 years old? Well, there's several people in the group, so what do we have to do? Well, we have to add those categories together. So if you add everybody between 25 and 54, I should say 2, right? Not and, but really 2. Okay, there is a 779 is what it should be. And what is the probability a randomly selected employee is not over 54? Well, if you look at not over 54, there you can add up the 4 categories for that, and that is going to be, so not over 54, that's going to be 833 over 1,000, which is 0.833. And the last one, what is the probability a randomly selected employee is not 15 to 24? Now this one, you could add all the other categories together, but if you think about the complement, if you do 1,000 minus 54 over 1,000, right, that'll give you the 946 over 1,000. So you may have added all the other categories, which I think that's 5 or 6 numbers to add up, but that's not necessarily the easiest way to do the problem. Now you might say that's not a big deal, it's adding 5 numbers together, but what if you had like 50 categories or 100 categories? It'd be much easier to subtract from the total, like here 54 subtracted from 1,000, than it would be to actually add all those categories together. Okay, so that was a lot. That's basically an overview of basic probability, so try to do the Math Excel assignment, and if you have any questions, then please ask.